Welcome back to Velocity Bite-Sized, a video series sponsored by Velocity that explains Kubernetes and cloud-native topics in bite-sized chunks of 10 minutes or less. I'm Jeff Vincent, a technical writer with Velocity, and today I'm going to talk about replica sets and deployments. Specifically in this video, we're going to talk about high availability in Kubernetes, and then we're going to talk about replica sets and deployments and how they make this high availability possible in Kubernetes. And then finally, we're going to walk through the process of defining and deploying a Kubernetes deployment. So let's get started. As we discussed in an earlier episode of this series, a Kubernetes pod is a fundamental element of compute resource in Kubernetes. So it is the smallest compute resource you can spin up. And again, its job is to run a container. And that all works fine so long as all of the infrastructure and the pod itself is healthy. But what happens if the pod is no longer healthy? Suddenly we have a scenario where the application that is running in that pod is no longer available to the users of that application. And this is where high availability in Kubernetes comes in. Kubernetes allows you to run exact replicas of the same application in different pods at the same time. And because of that, you have a much higher degree of confidence that even if one of those pods should fail for some reason, maybe it runs out of resources on the node that it's been deployed to, it could be any number of different things. If you have exact replicas of that same pod, then traffic can be rerouted to the healthy pods, and the pod that has failed can be torn down and spun up again because, as we discussed in an earlier video, pods in Kubernetes are ephemeral objects, which means that exact copies of that pod can be created and deleted any number of times. But managing all of these different copies of the pods and making sure that they're healthy would be tremendously complex for a human to do. It would take a lot of time and a lot of resources. And so to help with that, Kubernetes gives us this replica set object. And its job is to keep track of the exact number of replicas of a given pod that we want deployed at a given time. And it knows that by checking on information that is stored in a central database in Kubernetes called etcd. So when we submit a request to the Kubernetes API, and we say we would like 3 copies of this pod to be running, that information is stored in this central database. And that replica set is able to check on the desired state of the cluster. So if at some point we change the number of replicas that we want, maybe we want more, maybe we want fewer, it is able to, on the fly, continually check on our desired state of the cluster and reconcile the actual state of the cluster with what we've said we want running. And while you can deploy a replica set directly that will manage a certain number of pods for you, like we just described, the standard practice in Kubernetes is to deploy something called a deployment. And that deployment manages a replica set. And in turn, that replica set manages a certain number of pods. And in exactly the same way as we described for the replica set, the deployment knows the state of the replica set that we want because it's stored again in this central database in Kubernetes called etcd. So it can also continually check on the desired state of the cluster, and if we submit a change to that, say we submit another request to the Kubernetes API and we say we want to update the application, we are only having to interact with a single Kubernetes object, and it is abstracting away all the complexity of managing all of these additional relationships inside of Kubernetes. So if we want to update a deployment, we simply update a single resource in Kubernetes, and it takes care of the rest. And because of its ability to abstract away all of that complexity, we're actually also able to update the application while maintaining Kubernetes high availability. And that's because by default, when we submit a new desired state to the Kubernetes API, and that desired state is stored in etcd, the deployment will check on that new state, and it will start to make changes within the cluster so that it can align with what we've defined as our desired state. But it won't tear down the whole deployment at once and then rebuild it. Instead, it will do it incrementally so that while we are updating an application, we can still serve the old version until the new version is up and running and ready to go. This next part may seem a little bit complex, but hang in there, you'll get it. So, because the pods that are running our application can be created and torn down any number of times, and there are exact replicas of that same application running at the same time, we can't be sure which specific instance of that application a given user's request will be sent to. So, because of that, the applications need to be stateless with a deployment. And that means that you can't change the state of the application environment based on a user's action directly. Instead, the application needs to act as a pathway to some external storage point where you can store the data that resulted from that user's action. And we'll get into that in a later episode, but the key idea here is that because the pods can and will be created and deleted automatically in the background, they have to always remain the same. So if a user logs into your application, that login data cannot be stored inside of that running application instance. Instead, that data needs to be stored in some external database or some other mechanism within your Kubernetes environment. Because if that pod that stored that user's login data failed and was torn down and then spun back up, that user's login data would no longer exist. Likewise, if a user's request was sent to a specific instance of the application when he or she logged in, and then a subsequent request went to a different instance of that application, that login information wouldn't be stored there, so you would have a break in your application. So, in a nutshell, the applications running in a deployment need to be stateless. So now that we've covered the conceptual pieces of a replica set and deployment in Kubernetes, let's look at the practical piece of actually defining a deployment in YAML and submitting it to the Kubernetes API with kubectl. As you can see, we are going to submit a request to the Kubernetes API version apps v1. We're going to tell it we want to create a deployment, and we want to be able to refer to that deployment by the name Nginx server. And we're going to apply a label to that object so that we can later associate it with the replica set that it's going to manage. Next, we get into the spec section where we have selector and match label sections that contains this same label, app Nginx server. And this is how the replica set is going to identify the pods that it needs to manage. Next, we're going to give it a count of 3 replicas. So we want 3 identical pods to be spun up, is what this is saying. Then we get into the metadata of that replica set, and we say we want to apply the same label that we applied to the deployment above. So that's how they'll be associated. And then we get into this next spec section where we define the containers that we want to run inside of our pods. And we talked through the basics of a pod manifest in a previous video. So I'll just summarize here and say we're going to run a Nginx server in there with a specific image, and we're going to expose a container port from inside of the container to the pod itself. Next, let's look at the kubectl command we're going to run. We're going to run kubectl apply -f webserver.yaml because that's the name of the manifest we just created. We're going to get a response that says the deployment was created. And we can go ahead and check on the status of that by running kubectl get all. But as you'll notice, although the different objects that we've created, the deployment, the replica set, and the pods themselves, have all been created, they're not yet running because the pods need to pull the container image from a registry before it can start the process. But after we give it a second to spin up, we can run kubectl get all again, and we can see that our deployment is ready and that our Nginx pods are all running and healthy. I hope you guys enjoyed this video and learned something, and if you did, please like and subscribe below, and feel free to come and join the conversation in the Velocity Discord server. The link is below as well, and until next time, happy developing.